So we left off here on Friday. The example is a maglev train in Japan traveled at a record-breaking speed of 603 kilometers per hour. What is the average speed in meters per second? And how long would it take the train to travel 500 meters? So the maglev train is like a bullet train, but faster. It used magnets to allow a train to hover on the tracks and pushes it down the track very quickly. So we talked on Friday I guess all of last week on how to convert units. So let's take this 603 kilometers per hour and change it to meters per second. So for A, 603 kilometers per hour. We need to cancel the unit of kilometers, so we'll put it on the bottom and looking for meters. There are 1,000 meters in 1 kilometer, so the units of kilometer cancel. Now, if we're trying to cancel the units of hours, hours up top, minutes below, there are 60 minutes in 1 hour. The units of hour cancel. And we need to one more time cancel minutes and turn it into seconds. There are 60 seconds in 1 minute, and the unit of minutes cancel. When we multiply all the way across the top, we get 603,000, and the only unit left that we have not canceled is meters up top. And we divide that by 1 times 60 times 60, which is 3,600. The only unit we haven't canceled is seconds on the bottom. All right, putting that into our calculator, I get 167.5 meters per second. Given that there were 3 significant figures in our question, we need to report our answer to 3 significant figures. So 168 meters per second would be the appropriate answer here. For B, we're going to need to do a calculation. So like we talked about on Friday, we're going to divide our page into 3 sections. One where we are going to list our variables. The second one where we are going to choose an equation and rearrange if necessary. I think I should have had 2 O's there. And the last one is where we're going to plug in and solve. So from our question, we have an average speed. So that was V. And we had it in 2 units. So I'll write both units. So 603 kilometers per hour, or we had 168 meters per second. And depending on what other units I have, maybe for time or for distance, I will choose one of those values to input. The other value we were given here in B was how long would it take the train to travel 500 meters. My goodness. So we got the change in distance, or the distance traveled, and that was 500 meters. So because I have units of meters for a distance, I'm likely to choose meters per second for the units of average speed. The last thing I should write is what I'm looking for, and we're looking for the time. So again, we only have one equation right now, but when there becomes a few more in physics, it's really important to choose an equation that we have information for. So we have V and D, and we're looking for T. So we're going to choose the V is equal to delta D over delta T equation, but we need to rearrange it now for delta T. So because delta T is in the denominator, the first step is to multiply it out, and I'm going to cancel those. I'm left with delta T times V is equal to delta D. To get V by itself, delta T by itself, I'm going to divide both sides by V. That cancels V on the right, and I'm left with delta T is equal to delta D over V. And this is the equation I'm going to plug into and solve. So delta t is equal to, well, the delta D value that we had was 500 meters, so I'm going to put that in here. Again, using my units throughout. And the average speed that contains the same units would be our 168 meters per second. So, using my calculator, 500 divided by 168 meters per second, I get 2.97619, and the unit for this time is seconds in this case. Again, rounding to 3 significant digits or significant figures, I should round to 2.98 seconds. And this is my final answer, so I'm just going to circle it so that if it were being marked, the marker would know what my final answer is. Okay. So now that we know how to calculate, we also need to know how to graph. So a few things to note here. When we are representing data collected in an experiment or some sort of scenario, it's often recorded in a table of values. In the table of values, each title or column includes the name of each variable, its symbol, and the unit of measurement. Units are not included with individual measurements. That is important to note here. Okay. When we are graphing, the title is always in the form of y versus x. Remembering that when we are graphing, this is our x-axis and this is our y-axis. So whatever the title is along the y is what we would start with versus x, whatever the title was along here, followed by some sort of descriptive phrase that contains the context of the question. So we need to write a title every time. The axes of the graph, the independent or manipulated variable that is changed intentionally is placed on the x-axis. This often in physics ends up being time. So if time is part of an experiment, it's like 90% sure that you're going to put it on the x-axis. And in fact, in this class, I would say you're probably closer to 100% sure. The responding variable, so what changes because we are manipulating something, is placed on the y-axis. We label each axis with the name, the symbol, and the unit of the data being plotted. The scale of each axis should be set to use as much of the graph as possible. Try to use at least 2/3 of the graph space. So do not cram your graph into a small subsection here. You want to use the majority of your graphing space for your labels of the numerical parts of your axis and to plot your data. Scales should be easy to read and evenly divided. Don't go up by, 1 and then 3. Make sure it's very even. Count by 2s, count by 5s. Those are the easy ones to remember. Line of best fit. Don't just connect dots in a graph. That's more for experimental data. The rest of this data, it's going to be very clear what kind of line we're drawing. When we get to experimental data where the line of best fit takes a little bit more consideration, we'll take some more time to talk about it. But what you need to know is that if the graph is linear, we can calculate its slope to find different pieces of information. So the best way to do this is just to practice. So a motorboat is traveling at uniform speed. The boat masses a marker buoy placed 5 meters apart, which act as a measuring scale. As the boat passes the first marker or first buoy, a person on shore starts to record the distance the boat travels away from the first marker every 2 seconds. So they're just measuring the distance from the first buoy at specific time intervals. Noticing that time is here and distance from the first marker is dependent on how long this boat was traveling. Therefore, time is our x variable. It is our manipulated variable. And our distance from the first marker is the responding variable, how long it, or how far it traveled in a specific amount of time. So we're going to take that information and we are going to quite literally copy those into the labels for our axes. So I'm going to put time along the x-axis. Make sure you leave some room here so we can actually add some numbers for the scale. So time, and that variable is t, and the unit is seconds. Then along the y, I'm going to write distance from the first marker and that's d, the symbol, and it's measured currently in meters. Okay, then in our graph, we need to input the scale. So counting here, we need to go up to 10 seconds. So starting at 0, let's just count how much space we've got in our graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 seconds takes us to here, which looks pretty good. That looks like we've used about 2/3. Rather than writing 1, 2, 3, 4, 5, 6, 7, all of that clutters our scale. So instead, what we're going to do is we will write either in 2s or 5s, however you feel. So you could write every 2 lines what the scale is. It's very clear. Alternatively, you could write every 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4. That's 10. So it just makes it less cluttered. Same thing along the y-axis. Looks like this is 14 by 14. So I'm going to maybe count by 10. So 10, 20, skipping every second one. So 10, 20, 30, 40, 50. That puts me approximately here. That looks pretty good. That looks like I've used about 2/3 of my space. So I never want my scale to go over the top, okay? I can't just like draw any lines in. You have to stay within the available graphing space. So let's write those in. So 10, 20, 30, 40, and 50. So the scales don't have to be the exact same numbers. They don't have to go up by the same amount. We have gotten up to 10 for our X and 50 for our Y. We are ready to graph. Once we have this information, we're simply going to plot our values. So here we see 0 for X and 0 for Y. That puts us here. And then 2 for X, 10 for Y, puts us here. 4 and 20, 6 and 30, 8 and 40, 10 and 50. Okay, we can very clearly see that I could connect all of my points with a straight line. So a line of best fit would be appropriate here. The graph is linear and therefore we can calculate the slope. So using a ruler, make sure you calculate or draw right through all of these points. Okay, so I've drawn through my points with my ruler, connecting the dots in this case, drawing my line of best fit. All right, so that is part A done. Next, we need to calculate slope. Now, if you have not done Math 10 in its entirety yet. This might be new. So slope of the line is a measure of the rise between 2 points over the run. So in physics, we're going to choose 2 points that are reasonably far away on our line of best fit. So we'll choose maybe this point and this point. So point 1, the coordinates are 0, 0, and point 2, the coordinates were 10 and 50. So when we are measuring rise over run, we're measuring basically how steep this line is. Rise is how far we travel from point 1 to point 2, run is how far we've traveled from point 1 from point 2 in the x direction, and run is how far up it needs to go. So to calculate rise, we can calculate the change in the y value, and the run is the change in the x value. So we're going to take the coordinate from y2. So from point 2, we'll take the y value, take away y1, all over x2 minus x1. So final minus initial point. All right, from there, we're just going to substitute in what we know for those coordinates. So y2 was from point 2, the y value is 50, and the unit again is meters because we were measuring distance in the y. And we're going to subtract 0 meters because that's what we had for a y value here. Then divide by x2, which was 10. So this was 10 seconds because x was measured in seconds. Take away 0 seconds from our first point. When we calculate this, we get 50 meters over 10 seconds. And when we divide that, 50 divided by 10 is 5. I'm going to give it one more significant digit because of all of the data I was given. So 5 meters per second. All right. So if we look at this, we've calculated the slope. What does slope represent? Well, looking at the units of slope, meters per second describe average speed. So the slope represents average speed. And this again is because slope was equal to rise, and our rise units or information was distance, and our run was time, and distance over time was delta d over delta t, which we knew equaled velocity. So we can put the units or information back into our slope formula and decide what does this formula actually represent. It's average speed. So using your units can be very helpful to give you an idea here. The slope of a distance time graph is a visual representation of the speed of an object. The greater or steeper, oops, that's not a great color to see on the board, or steeper the slope indicates a faster speed, and a lesser slope or more gradual slope indicates a slower speed. So looking at the motion of each object in this graph here, we have lines 1, 2, and 3. Line 1 appears to be the most steep, if you were thinking about it as a hill to climb. So line 1 has a steep slope. Therefore, it is the fastest speed. in our distance time graph here. Number 2, the green one, the slope isn't quite as steep as line 1, but it's not quite as flat as line 3. So it's moving slower than line 1. So slope isn't as steep. As line 1. Therefore, 3 dots means therefore, it is moving slower than object number 1, whatever that was representing. Line 3 is flat. We can see that it is gaining no distance over time. If it is gaining no distance, that means it's not moving. If it's not moving, the speed is 0. So because slope is 0, it's flat, the rise is 0. So no rise in this one. For our slope equals rise over run formula. Therefore, the speed was 0. Okay, so let's continue with that same example of the motorboat. So suppose the motorboat mentioned previously is traveling past the same marker buoys. This time, a person on shore uses a radar gun to record the speed of the motorboat every 2 seconds. Graph the speed of the boat versus time. So once again, time is here. Time when the buoy passes the marker. Time will be our x-axis, and speed will go on the y. So, time when boat passes marker, and time is measured t, it's in seconds. And then making sure you leave room for your scale here. Speed of the boat, as it, I'm getting too close to the edge, passes marker, and that is speed, v, in meters per second. We forgot to put a title on our last graph. We should probably go back and do that after. We need a title. So this was the speed of the boat versus time as it passes each marker. So notice that we did y versus x, and then some sort of context. Okay, my scale for time is going to be the same because we're measuring over the same time period. Then I just need to figure out what I need for the y. So we just need to get up to 5. So I am also going to count by every second square, and I'll go up by 1s, 3, 4, 5, like instead of 10s like last time. Okay, and then plotting the data. So at time 0, it was going 5 meters per second. At time 2, it was 5. At 4, it was 5, 6, 8, and 10, it was 5. Pretty clear we could draw a line of best fit here. So we will draw one straight line and connecting those dots. Great. Okay, so in this case, our line is flat. Ooh, that's a thick line. Which means that as the time elapsed increases, the speed remains constant. So nothing has changed here. You can determine the distance traveled by calculating the area under the graph. So let's take a look here. So calculate the distance traveled by the motorboat in 4 seconds using the graph you created above. What we're going to do is we're going to draw a rectangle on our graph for 4 meters per second up to our line of best fit. So 4 seconds would be here. Technically, I would draw right up to that line. And I'm going to calculate the area under my line of best fit here. So I'm going to calculate the area of what turns out to be a rectangle, just the way it is. So from 0 to 4 seconds. So area is equal to length times width of our rectangle. The length of my rectangle, let's start along the bottom, is 4 seconds. And the width is 5 meters per second. I've included my units because this is very helpful to show me what I am calculating. So a second times in meters per second, seconds cancel. This would be because we have seconds times a meter per second. Seconds on the top and the bottom cancel. I'm left with just a meter. And 4 times 5 is 20.0, or I guess I should say just 20. And the unit is meters. So the area under the graph is just meters, and it shows that we traveled 20 meters in 4 seconds. The reason this works is, in our case, area is equal to length times width. The length we put in was time, and the width, or the height of our rectangle in this case, was the average speed. So when we rearranged V is equal to delta D times delta T, if we multiply both sides by delta T, I'm left with delta T times V, which is exactly, what we ended up with here. Therefore, our area was equal to what was left, or delta D. Okay, last little bit. You can do this, team. All right, so if the line of best fit in our previous graph, the slope of the line, was anything other than 0, it means that the object is changing its speed as time passes. You should probably change this. It's not delta D, that was V over T. Okay, so when we look at these graphs here, we see that we are plotting speed over time. Let's take a look at A. The speed of A starts here and it slowly increases over time. That means that our object is speeding up. Whereas in B, we take a look and our speed starts here and it is decreasing. So our speed is becoming smaller and therefore our object is slowing down or losing speed. All right. That is the end of our information today. I need you to take a look at some practice in your textbook to make sure that you're comfortable with this formula and with this big idea of graphing. We're going to do a lot more graphing. Now it's a really good time to start to get a handle on it because it might feel a little bit new. So I have some textbook practice for you, and that is page 128. These are the questions kind of in the middle of the page, number 1, 2, and 3. Page 130, number 4. I do believe that's a graphing example. And then kind of putting all of these ideas together and a bit of a topic review for this section. There's a lot more questions here. 4, 5, 6, 8, 9, 10, 11, 12, 13, 16, and 17 are some good challenge questions.